14.5 Fluid Dynamics. The outline of this video is as follows. We will begin by characterizing the two main types of fluid motion, distinguishing between smooth, laminar flow and chaotic, turbulent flow. This will set the stage for our main analytical tool. Next, we will introduce the ideal fluid model, a simplification that ignores complexities like viscosity and compressibility, allowing us to build a foundational understanding of fluid dynamics. We will then learn to visualize fluid motion using the concepts of streamlines and tubes of flow, which help track the movement of the fluid. Finally, we will derive and apply the equation of continuity, a key principle based on mass conservation that relates a fluid's speed to the area through which it flows. Up to this point, our entire discussion has been about fluid statics, the physics of fluids at rest. We will now shift our focus to the more complex and dynamic situations where fluids are in motion. This area of study is called fluid dynamics. The first crucial step in analyzing a moving fluid is to classify its behavior, because not all fluid motion is the same. Generally, we can categorize the flow into one of two main types. The first type is called steady or laminar flow, which is smooth and predictable. The second type is turbulent flow, which is irregular and chaotic. For example, think of a gently flowing river versus the rapids in that same river. Understanding the difference between these two types of flow is fundamental to describing how fluids move. To understand how fluids move, we first need to distinguish between two fundamental types of flow. The first, and simpler, type is called laminar flow. In laminar flow, each particle of the fluid follows a smooth, predictable path. A key feature is that the paths of different particles never cross, much like cars staying perfectly in their own lanes on a highway. The image of air flowing smoothly over the car in the wind tunnel is a perfect illustration of this orderly motion. However, if a fluid moves faster than a certain critical speed, its flow becomes turbulent. Turbulent flow is irregular, chaotic, and unpredictable. It is characterized by small, swirling eddies or whirlpools. You can see a clear transition in the smoke image, where the flow starts as smooth and laminar near the bottom, and then becomes chaotic and turbulent as it rises. The essential difference is that laminar flow is orderly and predictable, while turbulent flow is chaotic and unpredictable. Analyzing the motion of real fluids, like water or air, can be incredibly complex. To make the physics manageable, we start with a simplification called the ideal fluid model. A key property of real fluids that we often ignore in this model is viscosity. Viscosity is simply a measure of a fluid's internal friction. You can think of it as the resistance that adjacent layers of the fluid have to sliding past one another. For instance, honey has a high viscosity, meaning its layers resist moving, so it flows slowly. Water, on the other hand, has a low viscosity and flows much more easily. The ideal fluid model is built on four key assumptions that simplify reality, and the first assumption directly addresses this property. By defining this model, we create a foundation for understanding fluid dynamics, starting with the simplest possible case. The motion of real fluids can be incredibly complex. To make the physics manageable, we introduce a simplified model called an ideal fluid, which is defined by four key assumptions. First, we assume the fluid is non-viscous. This means we neglect all internal friction. Think of it like a fluid with zero stickiness, where layers can slide past each other without any resistance. Second, the flow is laminar, meaning the fluid moves in smooth, predictable layers or streamlines, without any chaotic swirls. Third, the fluid is incompressible, which means its density remains constant everywhere. This is an excellent approximation for most liquids, like water. Finally, the flow is irrotational. This means the fluid does not have any net rotation. If you were to place a tiny paddle wheel in the flow, it would move along with the fluid, but would not spin about its own center. These four assumptions form the basis of the ideal fluid model, which allows us to derive the fundamental principles of fluid dynamics. To visualize the motion of particles in steady, laminar flow, we use the concept of a streamline. A streamline is the specific path that an individual fluid particle follows. A key property is that the particle's velocity at any point is always tangent to the streamline at that same point. When we bundle a set of neighboring streamlines together, they form what we call a tube of flow. You can think of this tube of flow as an imaginary pipe whose walls are defined by the streamlines. In steady flow, streamlines cannot cross one another. This has an important consequence. Any fluid that enters a tube of flow must remain within that tube. No fluid can pass through the sides. This concept is incredibly useful because it allows us to isolate and analyze a specific portion of the fluid as it moves. The equation of continuity is a fundamental principle for fluid flow that comes directly from the conservation of mass. It explains how a fluid's speed changes as the pipe it flows through gets wider or narrower. Let us consider an ideal, incompressible fluid flowing steadily through a pipe. This means its density, which we label with the Greek letter rho, is constant. The pipe's cross-sectional area changes from an initial area, A1, to a final area, A2. In a small time interval, which we call delta t, a certain mass of fluid, M1, passes through the first area, A1. This mass is equal to the density times the volume that flows past. The volume is the area, A1, multiplied by the distance the fluid travels, which is its speed, v1, times the time interval. So, m1 equals rho times a1 times v1 times delta t. By the same logic, the mass m2 that passes through the second area, a2, is rho times a2 times v2 times delta t. Because the fluid cannot be compressed and no fluid is leaking out, the mass flowing past point 1 must equal the mass flowing past point 2. Therefore, m1 must equal m2. This equality of mass flow is the foundation of the equation of continuity. This slide introduces the equation of continuity, which is a direct result of mass conservation for a flowing, incompressible fluid. The core idea is that the mass of fluid entering a section of pipe in a given time must equal the mass leaving it. Because the fluid's density is constant, the volume passing any point per second must also be constant. This quantity is called the volume flow rate, and it is equal to the cross-sectional area, A, multiplied by the fluid speed, V. This gives us the simple relationship, A1 times V1 equals A2 times V2. The product A times V remains constant along the pipe. This has a very practical consequence you have likely seen with a garden hose. When you cover part of the opening with your thumb, you decrease the area A. To keep the volume flow rate constant, the water's speed V has to increase, making it spray out much faster. Therefore, the essential principle is that fluid speed is high where a pipe is narrow and low where it is wide. This example provides a great opportunity to connect our understanding of fluid dynamics with the principles of projectile motion. The problem asks us to find the horizontal range of water sprayed from a garden hose. To solve this, we must break the problem down into two distinct parts. First, we analyze the fluid dynamics inside the hose. We are given the volume flow rate, which is the volume of water that passes a point per unit of time, and the cross-sectional area of the nozzle. Using the equation of continuity, we can calculate the speed at which the water exits the nozzle. This exit speed will become the initial velocity for the second part of our analysis. Second, once the water leaves the nozzle, it is in freefall and behaves as a projectile. Its motion is governed by the laws of two-dimensional kinematics. The water has an initial horizontal velocity, which we found in the first step, and it accelerates downward due to gravity. Our overall strategy is to use the continuity equation to find the water's exit speed, and then use projectile motion equations to find how far it travels horizontally. To solve this problem, we will first determine the speed of the water leaving the nozzle, and then calculate how long it takes to hit the ground. Our first step is to find the volume flow rate, which we denote as I sub v. The problem states that 30.0 liters of water fill a bucket in 1 minute, and this gives us the flow rate directly. Next, we relate this flow rate to the speed of the water. The volume flow rate, I sub v, is also equal to the nozzle's cross-sectional area, A sub 2, multiplied by the water's exit speed, V sub 2. By rearranging this equation, we can solve for V sub 2. This exit speed is the crucial link between the fluid dynamics and the projectile motion part of the problem, because it is the initial horizontal velocity, V sub xi. Finally, we analyze the projectile motion to find the time of flight. Since the water is projected horizontally, its initial vertical velocity is 0. We know it falls a vertical distance of 1.00 meter. Using the kinematic equation for vertical displacement, we can solve for the time, that the water is in the air. We are now ready to calculate the horizontal distance the water travels before hitting the ground. This final step involves combining the exit speed of the water with its time of flight. The horizontal distance, which we call x sub f, is simply the horizontal velocity multiplied by time. We previously found that the horizontal velocity, v sub 2, is the volume flow rate, IV, divided by the nozzle area, A sub 2. We also used kinematics to find that the time of flight, t, is the square root of the fraction negative 2 times y sub f over g. Now we can substitute the numerical values into this combined equation. The volume flow rate is 30.0 liters per minute. The nozzle area is 0.500 square centimeters, and the vertical displacement y sub f is negative 1.00 meter. A crucial step here is to ensure our units are consistent. We must convert liters to cubic centimeters and minutes to seconds. After applying the conversion factors and performing the arithmetic, the final result is 452 centimeters. So, the water can be projected over a horizontal distance of 4.52 meters. Let us take a moment to summarize the foundational concepts of fluid dynamics we have just covered. We began by classifying fluid motion into two main types. Laminar flow is smooth and orderly, while turbulent flow is irregular and chaotic. To simplify our analysis, we introduced the ideal fluid model. This model is based on 4 key assumptions. The fluid is non-viscous, meaning it has no internal friction. It is incompressible, so its density is constant. Its flow is laminar, and its flow is irrotational, meaning it does not rotate. We defined a streamline as the specific path a particle follows in laminar flow, noting that the particle's velocity is always tangent to this path. Finally, we arrived at the equation of continuity, A1 times V1 equals A2 times version 2. This equation is a statement of mass conservation for an incompressible fluid. It tells us that fluid speed must increase where the flow area narrows, and decrease where it widens. These principles are the essential building blocks for understanding fluid behavior. To wrap up, let us check our understanding with 2 review questions. The first question is a direct application of the equation of continuity. Imagine a fluid in a pipe that narrows to half of its original diameter. By what factor does the fluid's speed change? To solve this, relate the change in diameter to the change in the cross-sectional area. A common pitfall is forgetting that the area is proportional to the square of the diameter, not the diameter itself. Use this relationship within the continuity equation, A1 times V1 equals A2 times V2, to find the new speed. The second question asks you to think about the bigger picture. We built our analysis on the 4 assumptions of an ideal fluid. But no real fluid behaves this way perfectly. Why then is this model so useful in physics? Also, what important, real-world phenomena, such as friction or turbulence, are we intentionally neglecting by making these assumptions? Thinking about a model's strengths and limitations is a key skill. Take a moment to work through these problems to test your grasp of the material.